Last time we talked about Ranguta methods, and then we talk about the truncation error, and then we try to define convergence based on the truncation error, and then we ended up with certain relationship which involves the real solution applied to the Ranguta method and the truncation error, right? And then we see that as we see in the other methods, right? So we see that we can think of using the Lipschitz condition to verify the convergence of the given Ranguta method, right? So we will continue from where we left, right? So this is what we have. Okay, so this is what you have when you incorporate the truncation error into the Ranguta method, and then you apply the real solution to that certain Ranguta method, right? So this is what you have, right? So then what we do is, then we introduce this, right? Okay, so then what we did is we introduce this notation tau of h, right, which is the maximum among all the truncation errors over all t, right? So that is how we define the tau, right? So okay, so last time we defined a variable called delta h, right, small delta h, and that is basically the supremum of the difference between small f and capital F, right, overall t, right? So we use that. So we see that we need to have this to be 0, right? So recall that. Okay, so this is what we learned last time. So what we did is we used the truncation error, right? So this truncation error is what we defined first, right? And then we see that this has to goes to 0 as it goes to 0 in order to guarantee the convergence, right? So that is the basic idea of convergence, right? So the error should goes to 0. So here the variable is h, the steps length. So you have to have h goes to 0. Sorry, yeah, when n goes to infinity, it goes to 0. So eventually this has to converge. But we see that by the way we define this tau n, we see that tau n goes to 0 is equivalent to f, capital F goes to y prime. But y prime is small f, we all know that is how we define the derivative, right? So clearly f goes to small f, capital F goes to small f as it goes to 0 is what we require to for the convergence. But capital F goes to small f is equivalent to delta H goes to 0, right? So in order to have this, you should have this. In order to have this, you should have this, right? Delta H goes to 0. So here again, if you know delta H goes to 0, then you know this goes to 0. If this goes to 0, then you know that maximum of tau ny will goes to 0. So the error tau h will goes to 0. Right? So the whole idea is basically depends on how you can make this capital F goes to small f, right? So that is how all the convergence are related to each other, right? Basically to the convergence of the method. Right? So now what we are going to do is we are going to see how we can implement the Lipschitz condition into this, right? To see the convergence of delta H. Right? So that's how we are going to continue. Okay, so now what I'm going to do is I'm going to start assuming. Right, so let me suppose that F satisfies a Lipschitz condition, right? So that Lipschitz condition you can say that as follows. Right, so this is the Lipschitz condition. So the Lipschitz condition on the second variable y, right? So let us suppose that the function capital F satisfies a Lipschitz condition on this, right? So then on the other hand, So we basically assume right. So this is the very first thing we studied, right? We assume that the function small f satisfies a certain Lipschitz condition to ensure the existence of a solution for the initial value problem, right? So this is you studied in differential equation as well, right? But here also in this course, when we start talking about numerical solutions of differential equation, we say that for the existence of the solution, we require the function f to satisfy the Lipschitz condition, right? So that is one thing you remember. So basically, you will have two types of Lipschitz condition, right? So here you are supposing f satisfies the Lipschitz condition, but at the same time, you assume that you can automatically assume that small f also satisfies a certain Lipschitz condition. Right. So in that case, let's consider this, right? So now we notice that okay, so you notice this. So if you notice this, you can see that Okay, so what we do is we know that we have to assume that the function capital F should satisfy a Lipschitz condition in order to guarantee the convergence of the numerical method, right? So that we are going to see how we are going to do it later, right? Say for example, right? So, but you know that obviously this one is always true, right? So the small f will satisfy a Lipschitz condition with a certain Lipschitz constant k, right? So here because I use L on the other one, so I use k here. That's the Lipschitz constant, right? So this is always true. So how you can set up a Lipschitz constant for this case, right? For this capital F. So for an example, if you recall the example we did at the beginning of the Ranguta method, we derive a Ranguta method of order 2, right? With B1, B2 and beta and gamma as the constants, right? And then we choose different values for B2, and based on that we can find different numerical methods. So one of the methods we use is B2 is equal to 1. So in that case, we derive a method. You remember which look where the capital F looks like this, right? So for that example, let us see whether we can derive a Lipschitz condition or not, right? So we can do that because your capital F is this, so capital F of Z is this, and when you subtract, so since small f satisfies a Lipschitz condition, it is less or equal to k times the second variable difference in the second variable. So here the difference in the second variable is y minus z times y minus z plus half h times f of y minus t of f of z. But again, f satisfies the Lipschitz condition, so you apply that again. So you will eventually get k times 1 plus 2, 1 plus half hk times y minus z, right? So as long as the right, so in this case, if you choose your L as k times 1 plus half of h times k, then that means, right, right? So we can say capital F satisfies Lipschitz condition, and based on that, we can try to derive the right. We can always try to derive a convergence condition based on that, right? So this is just an example of how you can use the Lipschitz condition on small f to derive a Lipschitz condition on capital F, right? So that is the example. So now based on this, let us try to prove the convergence of the result, right? Okay, so now let us start writing the convergence results as a theorem first. Okay, so this is the convergence theorem, right? So we write down everything in one theorem, right? So we first derive an error bound, right? So this is the maximum of error. So error bound here. So we assume that we take the given Ranguta method, which we assume at the start of the section, and then we assume that it satisfies Lipschitz condition with Lipschitz constant L, the capital F, and then we say that the error bound for this approximation of y at Tn by Yn is given by this. It's very similar kind of results we derive for Euler method as well. If you recall that, we derive very similar kind of results for Euler method as well. And then if the method is consistent, right, which is what we proved in the last class, right, the consistency condition, right? So eventually we take tau n over h goes to 0 as h goes to 0. That is a condition, and we see that that is basically equivalent to this delta h goes to 0, right? So I just simply write it down as delta h goes to 0. Right? If the consistency condition is satisfied, then we see that we can prove that the method is convergent as well. Right? So this is the result. So let us try to prove this result. The first one, you need to prove that maximum of y of Tn minus Yn is less than this. So you have to find Yn minus y of Tn, or y of Tn minus Yn. So then what you do is you have the following, right? Okay, so you have these two equations, right? The first one is when you apply the real solution to the numerical method, then you will have the truncation error also. Right? Second one is basically the numerical method. So when you subtract one from the other, right? So I'm using a new notation. Right, so basically first you have to find the error bound, so you try to find the error. So in this case, you have Yn plus 1, Yn of y of Tn plus 1 minus Yn plus 1. So when you subtract, you get En plus 1 and so on. So you have this relationship, right? So based on, you take the absolute value, right? And then you use the Lipschitz condition, right? I'm going to write it straight away, but you can understand how it comes. Okay, so here you take the absolute value, and then what you do is you apply the Lipschitz condition here, right? So obviously you will get h times L times Yn minus Yn, so h times L times absolute value of En. And then for this, you take the maximum of tau n. The maximum of tau n is basically equal to tau of h, right? So this is what you have here, right? So a very similar type of recursive inequality we had in Taylor's expansion as well, right? So I am not going to explain you how we did this, but by continuing this recursive inequality, right? And also we see this in Euler method as well, right? So you can easily see that, right, by applying this inequality recursively, you should be able to get the required results there, right? So the work is very similar to Euler method from here, right? So right, so just a hint, it is very similar to what we did in Euler method. So you can again start applying this recursively and try to get the required condition for the error bar, right? So that is what we had there. Right, so now what we are going to do is now we are going to see that if the consistency condition is satisfied, then we are going to prove the convergence, right? So let's prove the convergence here. Right, so this leads to the result, so you know that how to do it. So I'm skipping that part now. Right, so next. This is how you define tau n of f, right? So it is basically the truncation error divided by h. So h times tau n of y is yn plus 1 minus yn. So basically this is the truncation error, right? Tau n by you define as truncation error divided by h. So that is what you see as the consistency condition there, right? So that's how you do this. So now what you are going to do is you are going to see the equivalent form, right? Okay, so this is what you have, right? So how do you get this? Is by applying the Taylor's expansion for ytn plus 1. So ytn plus 1 Taylor's expansion is ytn plus h times y prime tn plus h squared times h squared over 2 y2 prime and h cubed over 3, sorry, h cubed over 6 y3 prime, and it will continue like this. But you can approximate the Taylor's expansion with second derivative term, right? So this is what you do, right? So you know y tn plus 1 is basically y tn plus h times y prime tn plus what you do is h squared over 2 factorial time by 2 prime of psi n. So you approximate the y n plus tn plus 1 with the second derivative of the Taylor's expansion, right? So you write the Taylor's approximation basically. So when you substitute that, you get h yn by tn cancelled out. So you ended up with h times y tn by prime tn and h squared times by 2 prime and then the capital F term, right? So this is what you have for h of tau n. So now what we are going to do is we are going to take the absolute value of this or the norm of this. Okay, so here what you do is this, right? So you ended up with this, right? So h times tau n of capital Y is basically equal to this, right? So h times y prime is small f, right? Remember h times so small f of tn comma capital Yn, right? And then there is this here, so minus capital F of tn comma y of tn h of small, and so then f, right? So you have this minus this, right? So you factor out h and y prime is f, so you can do that, right? So that's fine. So this is y prime of tn, so tn comma y, right? And then there is h squared over 2 y2 prime of, right? So you take the absolute value and then take the maximum or infinity norm, right? So absolute value of this is this, less or equal to absolute value of this maximum is what we define as delta, right? Absolute value of this difference maximum is delta, so that turned out to be delta, and maximum of this is basically infinity norm, right? So you have this. So then clearly you can see that if h goes to 0, right? So if h goes to 0, right? So there is no h here because h times this is what we define as delta h, right? So that's how we define it. So fine. So you ended up with, sorry, this is, there is an h, right? So from this, what you have is tau n of y absolute value is less or equal to delta h plus h over 2 y2 prime infinity, no. Okay, so this is what eventually you have, right? When you cancel out h, you ended up with this. And from this, you can see that as h goes to 0, this clearly goes to 0, right? So this will goes to 0 as long as delta h goes to 0, right? So that is why you need to have, so this, from this, you can say maximum of this is basically tau of h, right? So when you take the maximum of this over all Tn, then this becomes Th, right? Tau h, that is less or equal to delta h plus h over 2. This is y2 prime of infinity. And this goes to 0 as it goes to 0 if delta h goes to 0. Right? So if delta h does not goes to 0, you cannot guarantee, or it is not guaranteed that this will goes to 0, right? So as long as delta h goes to 0, this will always, sorry, this is h. If this will always goes to 0 as h goes to 0, but as long as this goes to 0, this will goes to 0. If this goes to 0, then you know the truncation error goes to 0. Basically, the whole error term goes to 0, right? Remember, the error term goes to 0. So the numerical solutions converges to the real solution. So this is how we prove the convergence of the results by using the consistency condition and the error bar, right? So in the next class, what we are going to do is we are going to see a corollary of this results, and then we will talk a little bit more about the order and other concepts of the Runge-Kutta method, right? So about that we will start talking in the next class on Monday. Right? So I will stop here, and then we will continue on Monday with the corollary of the theorem, and then we will talk about order of these. Right? So let's stop here and then continue on Monday.